Okay, everyone, it's time for part 2 of related rates. So, say we have the length L of a rectangle decreasing at a rate of 2 centimeters per second, and the width is W is increasing at a rate of 3 centimeters per second. So, yeah, we seem to have a magically growing rectangle. Okay. So, when L is 12 and W is 5, find the rates of change of the area and also the length of the diagonal. So we have actually two separate problems entirely here. So yet again, I am going to draw a picture and label the variables. So I have a rectangle. It's fancy. And I'm going to call that W and L. And then once again, I will list the know, want, and when. So the things that I know, and by the way, the knows and the whens kind of get blurry a little bit, and that's okay. You just want to list them out so you have them conveniently, because like looking at all this text is a lot harder to look at than just having, just the knows, wants, and whens in a really little space. So I know the length is decreasing at a rate of 2 centimeters per second. So that would be dl dt. And watch this carefully, because since it's decreasing, that rate is actually negative 2 centimeters per second. I also know the width is increasing at a rate of 3 centimeters per second, so dw dt is 3 centimeters per second. And the thing we want, there's two things we want, is the rate of change of area. So for A, we want dA dt, assuming A for area. And then for part B, which we'll come back to, but that will be the length of the rate of change of the diagonal. I don't want to use D for diagonal, by the way, because then when I'm deriving, I'll end up with like D, T, and oh no. So we'll come back to that. Let's just deal with part A first. So, and then the when, that's going to be when L is 12 and W is 5. Having this listed, though, like looking at what I have written here versus having a paragraph, it's just a lot less to look at. Okay, so I have my picture. I've listed my know, want, and when. Writing an equation relating the variables, and I'm only looking for part A here, talking area. Do we have anything that relates area and width and length? Well, yeah, duh. So we have area is length times width. Just going to come over here. So that seems easy enough. So deriving with respect to time, we have to be really, really careful here, because L is a function, and W is a function. They're variables. We have a product rule here. So really, we have a U is L, U prime is dL dt. V is W, V prime is dW dt. So the derivative of LW is not just dL dt times dW dt. You have to product rule that, and so really be careful there. So taking the derivative with respect to time, the derivative of A, dA dt. Hey, that's the thing we want. It's nice that it's showing up. And then the derivative of L times W, derivative of the first, so dL dt, times the second, which is W, plus the first, which is L, times derivative of the second, dW dt. And solve for the desired rate. The thing we want is dA dt. It's already solved for. That's awfully convenient. So we can just plug in numbers and answer the question. Sounds straightforward. The thing to watch on this question is the fact that, yes, you have to product rule that. Just like you have to chain rule if you have, like we saw in the last example when we had the radius getting cubed. So all those rules we've known already, they're still here. So that's what makes, another thing that makes this so hard is having to pay attention to all the things. So dL dt, and having these listed out, remember, makes it just way easier to chuck things into place. So dL dt, negative 2, times W, which is 5, plus dW dt, L, which is 12, times dW dt, which is 3. So we have negative 10 plus 36, 26. And then remember, we want to answer the question with units. We use words and everything. So when L is 12 and W is 5, the area is increasing 26. And since this is area, our units would be centimeters squared in how we write it, but we say square centimeters per second. So there's our part A. Part B, looking at the length of the diagonal. So going back to my drawing, I'm going to throw my diagonal here. And we need to give this a variable. I'm just going to call it x. Again, I don't want to call it d because dt is just sounds a little too much like pesticide. Not going to have that. So do we know anything that relates those three variables? Of course we do. Let's come over here. We have the Pythagorean Theorem. 2l plus, I can write and speak at the same time. L squared plus w squared equals x squared. So the thing we want then is dx dt. And it's again when L is 12 and W is 5. So that's okay enough. If you want to throw that L and that W and that X into parentheses as a reminder about our chain rule, derivative of the outside. So the 2, keep the inside the same. The L times the derivative of the inside, dl dt. Chain rule. And then 2w dw dt, same logic, and 2x times dx dt. So on all three of those, we have the chain rule happening. Notice we have 2's and all of that. I can divide everything by 2, convenient. And while I'm at it, I can divide both sides by x because the thing we want, dx dt. So I have L times dl dt plus w times dw dt divided by x equals dx dt. So we've solved for the thing we want. And then finally plugging numbers in. And you might be going, wait a second. Because we have L, we have dl dt, same for w dw dt, but we don't know x. Oh no, what can we do? Oh, we can just use a Pythagorean theorem because 5 squared plus 12 squared happens to equal 13 squared. If you don't believe me, do the Pythagorean theorem. Or you can trust me. Your call. So 12 times dl dt, which is negative 2, plus w, which is 5, times dw dt, which is 3, divided by x, which is 13. There is our rate of change, which that simplifies to negative 9/13. So does it seem weird to you that this could be getting smaller? Well, it makes sense that it could get smaller or bigger, given that since L is getting smaller, depending on where things are in the state of rectangle flux, if that's a thing, it works. So, so remember when you're answering the question, since we are humans, we don't want to say something changing a negative amount. We will say when L is 12 and W is 5, X is decreasing. And we don't say it's going to decrease negative 9/13 because if you decrease a negative, wouldn't that mean increasing? It doesn't make sense. So X is decreasing 9/13 centimeters per second, and our units would be centimeters for X, seconds for Y. Time, rather. And there we go. So again, if you want to see more examples, just search on Khan Academy, YouTube, wherever. Just search related rates calculus, and you can watch any of the 11 million videos that are out there.